Okay, I'm back, and now we want to talk about what are some problems with telescopes and how do we fix them. So the first problem is stars are very dim. And so what we want to do is to be able to see these stars even though they're very, very dim. Now, what would be some solutions to this? Okay, one, collect as many photons being given off by these stars as possible. So one way of doing this is the longer the amount of time that do you remember we talked about the CCD, the charge coupling device? So that's the photographic plate on which the photons of light are going to be hitting. And then as those photons accumulate, it's going to give you a picture of the star. So the longer the amount of time that you hold the plate out and it's absorbing all of these photons, the brighter the image of the star is going to be. Another thing is if you can't control the amount of time that the photons are hitting, well, could you control the number of photons that are hitting the plate? Yes, you can by having a larger telescope. So the larger the telescope, the more photons hit your CCD. So bigger is better. We want to have as large of a telescope as possible. So this particular telescope shown in this picture is at Arecibo. So it's on an island in the Caribbean. So you might recognize it as being the set that they used for a particular James Bond movie where the villain had a laser that he was controlling using this particular facility. Okay, it really doesn't control a killer laser in outer space. We're going to find out at the end of this video series that this particular telescope was used in sending information into outer space about humanity in hopes that we would be able to contact alien civilizations. And we're also listening for alien communications as well. But this is a very big telescope. So if you look at that one, the size of that telescope, I think, is about 100 meters across. And so that is so big that you can't build any kind of an apparatus that would be able to turn the telescope. So the telescope is basically fixed in place, but as the Earth is rotating, you see that the telescope is turning. And then by using that thing up there above it, they can also alter the direction that the light is coming in from and so forth. So that is a telescope design problem. We want to try to gather as much light as possible, and we can do it by using a bigger telescope. Okay, another problem with telescopes we said was diffraction. We don't like diffraction. When it comes to light coming down the barrel, it spreads out and then it gives us the stars look blurry. So one solution is bigger is better. So have bigger telescopes. So the bigger the size of the telescope, the opening, the less diffraction you're going to have. We can use smaller wavelengths of light. And now sometimes you can't do that. So maybe you're really interested in radio waves. And radio waves are the worst as far as diffraction is concerned. But sometimes you could use a different wavelength of light, like visible, which is much smaller than radio waves. And so it's not going to diffract as much. The third way that we could do it is by using what's referred to as an array or an interferometer. And so that's when we use multiple telescopes to look at the same object. So let's take a look here, and let's say that you've got a telescope that is that big around. Well, that can let in a lot of light, but let's say that you've got two telescopes that are looking at the same star. If you hook these two telescopes together using a computer, it's equivalent to having a telescope that is that big. So it's a telescope that would have a diameter that is the distance between those two telescopes. Much, much larger. And then if you had another telescope over here, that would be equivalent then to having a telescope that would be about that big. So it could be humongous. So theoretically, if you had a telescope in Los Angeles and then a telescope in New York, and they're looking at the same star, then that's the equivalent of having a telescope that is how big? The size of the United States. So it's complicated, but it can be done by using multiple telescopes looking at the same object, hooking them all together, and this is known as an array of telescopes or an interferometer. Another problem with telescopes is light pollution. So here in Springfield, Missouri, if you go out at night and you look up at the sky, chances are you're not going to be able to see that many stars because there's so many street lamps and car headlights, and it just kind of blocks it out. We call that light pollution. So the local college here, MSU, their major telescopes are located like 27 miles away from Springfield in Marshfield. And out there, it's pretty dark. And so it's so dark out there, you can even see the Milky Way. So the rule then is to take your telescope and put it away from cities so you don't have to worry about light pollution. Another thing, though, is air pollution. So look at that picture there. What city is that? It's not in the United States. It's in China. That's Beijing. And so that is a bad day in Beijing because they have so many coal-fired power plants. They have a lot of pollution, and so you can see that that air pollution would obscure your vision of the stars. So what do? We take our telescopes, we move them above the clouds. So that second picture there, where do you think that is? That's in Hawaii. So they actually took a telescope and they mounted it basically on top of one of the volcanoes. And so it's dormant volcanoes. And it's above the clouds so that when they look up at the sky, they see a very, very clear view of the sky. Okay, another one, though, is problems with different kinds of light. Our atmosphere blocks certain frequencies of light. This is actually good because our atmosphere blocks gamma rays. And if those gamma rays got through, we would all be, you guessed it, Incredible Hulks. No, we'd be French fried from the radiation. Okay, X-rays, same thing. So our atmosphere blocks X-rays from getting to the surface of the Earth. It also blocks some of the ultraviolet because you know you can get a sunburn. So that some of the ultraviolet is blocked, but some of the ultraviolet makes it through to the surface of the Earth. Visible light, yeah, so visible light definitely gets through our atmosphere. And then most of the infrared, no, it doesn't make it. And but radio does. So we have these two, they're called optical, or they're called windows. So we have one that's the optical window, which is going to be your visible light and just a little bit of the ultraviolet. And then you got the radio window where the radio waves come through. So that's great if you want to look at the stars using visible light and radio waves, but what about if you want to use X-rays or gamma rays? Well, you're going to have to take your telescope and put it into outer space. So we have a telescope that is capable of seeing into the X-rays. Another kind of telescope can see into the gamma rays. Another kind of telescope can see into radios. The Hubble can actually see into a lot of the different parts of the electromagnetic spectrum. So, who cares? Well, I'll come back in the next segment and let's talk about that.